The hydrogen bomb is a staged thermonuclear weapon capable of terrifying amounts of destructive power. The United States moved forward with the hydrogen bomb as a response to the first Soviet atomic bomb test. Remarkably, the Soviets had their own H-bomb just 3 years later. We know that the Soviets benefited from spycraft to make that first A-bomb. Obviously, it's the same case for the H-bomb too, right? Not quite really. In this video, we look at how Soviet scientists found their way to the hydrogen bomb. But first, this video is brought to you by the Asianometry Patreon. Early access members get to see new videos first and selected references for those videos. Early access really helps me a lot, and I appreciate every pledge. Thanks, and on with the show. In September 1941, the famed Italian physicist Enrico Fermi presented an idea to the equally famed Hungarian-American physicist Edward Teller. The role of Edward Teller was played by Benny Safdie in the recent Oppenheimer movie, which I enjoyed. The accent seems pretty accurate. Anyway, while lunching with Teller, Fermi pondered aloud whether the atomic bomb, which was then in production, can be used to jumpstart a deuterium weapon. Such a weapon would derive its energy from fusing hydrogen into helium, releasing a much larger explosion than what you can get with mere fission, at least in theory. There are claims that a Japanese chemist at the University of Kyoto named Tokutaro Hagiwara first came up with the idea, supposedly mentioning it in a lecture in May 1941, but later translations imply that he was referring to something else. Teller soon became obsessed with this idea and pushed for its implementation. A team at Los Alamos started talking through the theories in the summer of 1942. At the time, it was believed that the fission bomb would be an easy job. After that was done, work can move on to the super, as it was called. The whole thing might even be finished before the war's end. But the A-bomb turned out to be far more difficult to implement. So, for the next few years, they spent most of their resources on the A-bomb. Teller, meanwhile, largely worked on his own, with occasional help from others. At the start, the idea was that neutrons and heat emanating from a fission-based trigger bomb detonation can initiate a subsequent nuclear fusion detonation in a mix of hydrogen isotopes. To implement this, you would take a gun-type fission bomb and a cylinder of deuterium. Deuterium is a relatively plentiful form of hydrogen with just one neutron in its nucleus. It is normally a gas, but takes a liquid form when sufficiently chilled. As those atoms fuse, they throw off more heat energy that propagates throughout the cylinder. A chain reaction occurs, eventually releasing as much energy as 1,000 fission bombs. A secondary perk, if you want to call it that, was that you can arbitrarily scale up the power of the nuclear fusion explosion by adding more deuterium. And that's scalable because deuterium is relatively plentiful in nature. Problems with what is called the classical super concept quickly came up. To start, a pure deuterium-deuterium reaction would require hundreds of millions of degrees, more than what even an A-bomb is capable of. Hot. So the physicist Emil Konopinski suggested adding tritium, a different hydrogen isotope. The idea was that tritium can act like lighter fluid for a campfire, the thinking being that deuterium-tritium reactions might more easily react than pure deuterium-deuterium. Unfortunately, tritium is also far rarer than deuterium. It has to be produced in nuclear reactors. The team worked on an approach to get around this tritium supply problem. By the end of 1945, the team had crafted and presented the classical super concept to their colleagues. People didn't need to debate about whether they had to make the A-bomb. The Manhattan Project people felt that they were locked in a race with Germany. Its secrecy was to make it so that the Axis powers would not be pushed into accelerating their timelines. Then in August 1945, the United States dropped 2 atomic weapons on Japan. World War II had ended, and the United States had been left with a nuclear monopoly. The world was now seemingly at peace. Why was there any need to produce a bigger bomb? But as the Manhattan Project wound down, there still kicked around the idea of the classical super. In the spring of 1946, a British scientist of German origin named Klaus Fuchs rotated onto the project after finishing his tasks on the detonation systems for the atomic bomb. Since his youth, Fuchs had been an active participant in communist organizations. In 1932, he joined the Communist Party in Germany, which was the most significant political group resisting the Nazi rise. That is how he came to Britain in the first place. He fled when the Nazis won power in 1938. Such a history did not prevent him from getting admission to the Manhattan Project in 1944. He was never considered a first-tier worker there, but had a gift and worked hard. Fuchs made a few improvements to the classical super concept. His thinking was this: if fast-moving neutrons were important to creating a fusion reaction, then it might make sense to encase the deuterium-tritium mix in a radiation-impervious cladding to keep as many neutrons inside as possible. This early conception of what we now call radiation implosion was later patented in concert with John von Neumann. Radiation implosion would later play a key role in the final successful thermonuclear bomb design, but nobody knew it at the time. In June 1946, Klaus Fuchs finished his contribution to the classical super and then left the Manhattan Project for Britain. After his return to the United Kingdom, it was discovered that he had passed over to the Soviet Union critical information on the atomic bomb's design and construction. He was imprisoned for 8 years before being released to East Germany. The Soviet Union hosted an excellent community of nuclear scientists prior to 1941. They would have gotten the atomic bomb eventually, but Fuchs's reports accelerated their progress by at least 1 to 2 years. Did he give the Soviets the keys to the hydrogen bomb as well? Now we turn our attentions away from America to the Soviet Union. In September 1945, scientists in the Soviet Union began receiving intelligence reports about the classical super design. Several Soviet physicists had already begun exploring the idea. One sent a memo that same month to Igor Kurchatov, scientific director of the nuclear program. The memo detailed the idea of using the atomic explosion's intense heat to produce helium from hydrogen, tapping the energy source of the stars. It was a fantastic insight, but nowhere near useful for practical use. The intelligence reports coming over from the United States detailed the progress of the classical super design as it was in late 1945. A uranium gun-type atomic bomb as the trigger, along with containers of deuterium and deuterium-tritium. The intelligence report also included Fermi's lectures about the physics behind the weapon and a note on tritium's role in triggering fusion by reducing the threshold temperatures. Support for building a Soviet super gained traction in October 1945 when the London Times reported remarks by Professor Marcus Oliphant. Professor Oliphant had said that it was possible to make a 2 megaton TNT equivalent bomb 100 times larger than the ones dropped on Japan, a super bomb. Now curious, the Soviets added the super bomb question to a list of questions for Niels Bohr. Bohr, played by Kenneth Branagh in the Oppenheimer movie, had recently returned to Denmark from the United States. He was puzzled by the question, saying, "What does it mean, a super bomb? This is either a bomb of a bigger weight than the one that has already been invented, or a bomb which is made of some new substance." Well, the first is possible, but unreasonable because, I repeat, the destructive power of the bomb is already very great. And the second, I believe, is unreal. Bohr's skepticism aside, the American intelligence reports were enough. The Soviets were already behind in atomic bomb technology. The Americans not only retained the atomic monopoly, they were working on something even more powerful. The Soviets had to pursue this idea. Kurchatov thus assigned a working group led by the Belarusian Yakov Zeldovich to examine the possibility. In December 1945, the group reported their findings. This brief document, titled Utilization of the Nuclear Energy of Light Elements, confirmed the possibility of a nuclear fusion bomb. The group was ordered to continue refining an approach towards such a weapon. New reports came to the USSR throughout 1946 and 1947 about American work on the, quote, super bomb, augmented with reports in the press including a 1947 article in the Bulletin of Atomic Scientists by Edward Teller. In September 1947, Fuchs, who recently returned to the United Kingdom, met with a Soviet intelligence officer. He told the officer that Fermi and Teller were working on a super bomb over in Chicago and that it was feasible, but he had no idea whether the Americans were actually going to do it. He explained some of the operating principles as he knew it, which included the use of a mix of deuterium and tritium. In November 1947, the Yakov-Zeldovich group came back with their findings. Their best idea was to propagate a massive shockwave through a batch of thermonuclear fuel, a mixture of deuterium, tritium, and lithium. This appearance of lithium was apparently included because of another intelligence report. The USSR Council of Ministers accepted this and established an office called the Designing Bureau 11, or KB-11, in the secret closed town of Sarov. Zeldovich and his team headed there to work. Shortly thereafter, in March 1948, Fuchs met with his intelligence handler and passed over documents with a detailed discussion of the American superbomb design with its radiation jacket. The documents were swiftly translated and sent to Stalin and Lavrentiy Beria, head of the NKVD. Alarmed by the seemingly advanced progress that the Americans had made, the two pushed for the acceleration of the creation of alternative nuclear bomb designs, like the H-bomb. In April 1948, Beria sent the documents to Kurchatov and others in the inner circle with instructions to carefully study them. In June 1948, the Council of Ministers passed a resolution for KB-11 to do feasibility studies on a new type of hydrogen bomb. Fuchs's design became the basis for the tube design, or RDS-6T. Meanwhile, director Igor Kurchatov asked the esteemed theoretical physicist and Nobel laureate Igor Tamm at the Lebedev Physical Institute to check Zeldovich's work. Tamm agreed because he believed that the Soviet Union as a nation needed to have nuclear weapons, despite some misgivings about their country's leaders having such things. He recruited a group of young physicists, including a theoretical expert named Andrei Sakharov. Tamm, Sakharov, and his colleagues did not like the Zeldovich design and began working on their own. By 1948, Sakharov had a promising design which he called the first idea. He did not have access to the superbomb documents passed over by Fuchs. The June 1948 resolution merged the two teams at Lebedev and KB-11 together. Sakharov deemed the special worker got his own apartment, which is nice. Anyway, Sakharov's design, eventually named RDS-6S, was called Sloika, which literally means layer cake. The name hints at how it works. Much of the details are still classified, but what we know indicates that the bomb was a sphere about 1.5 meters wide and 4.5 tons. That makes it the same size of the original Soviet atomic bomb, or the Fat Man bomb dropped on Nagasaki. Inside we have layers of highly enriched uranium as well as a thermonuclear fuel made from a mix of lithium deuteride, which is a solid compound of lithium and deuterium that kind of looks like chalk, lithium deuteride tritide, which is a variant of lithium deuteride but with tritium also mixed in, and uranium tamper. Tamper refers to the fact that it encases the fuel layers in order to delay the ongoing nuclear explosion and maximize the yield. These layers are surrounded by lenses made from powerful chemical explosives to compress the layers. The uranium in the outside layers trigger fission explosions of their own. The inclusion of the lithium deuteride came at the behest of Vitaly Ginzburg. He pointed out that the lithium in lithium deuteride, when bombarded with neutrons, can create more tritium, which is more fuel for the fusion explosion. This is referred to as the second idea. The end result is a very large fission, fusion, fission, boom, boom that is about 80% fission and 20% fusion. Tamm and Zeldovich both agreed that the Sloika design had the most potential as compared to the tube/RDS-6T and decided to focus their work towards building it. This all took place in 1948, before the first Soviet atomic test in August 1949. Unlike in the United States, there was no question as to whether or not they should go ahead with a bigger bomb. Soon after shipping the atomic, they took a 2-week break and went back to work on their hydrogen bomb. Note about this hydrogen bomb, one can't quite call it a real thermonuclear bomb. Yes, it did harness nuclear fusion to generate energy, but, at the risk of sounding like a pedant, most of its total energy came via fission. You would probably call it a boosted fission bomb, where the fission explosion creates thermonuclear reactions, which in turn creates neutrons that help increase the efficiency of the fission explosion. By comparison, the proposed thermonuclear superbomb, the classical super concept, is where the fission bomb jumpstarts a far larger thermonuclear explosion, two distinct stages. After the war ended, Oppenheimer was skeptical about the technicals of the classical super, correctly so as it turned out. He instead suggested the development of boosted fission weapons as a stopgap. Teller, for his part, wanted to go all in with the thermonuclear weapon. The first Soviet atomic bomb test, RDS-1, changed the conversation. The Americans not only realized the end of their brief nuclear monopoly, but also doubted their ability to predict the speed of progression of the Soviet nuclear program. There was a great debate on how America should respond, which I shall skip over. In the end, in January 1950, U.S. President Truman orders the accelerated development of the superbomb. The order hits the news and travels all over. The key issue with achieving a staged thermonuclear weapon, the idea that everyone has been pursuing since the very beginning, is this. It takes a massive amount of energy to get the deuterium to fuse together. How are we going to deliver enough energy to that deuterium and reach that trigger point before it dissipates away? As Edward Teller and his team worked on this problem, the Soviets were responding to Truman's order to build the superbomb. Zeldovich and his team present the RDS-6S design and are authorized to move forward with a prototype by May 1952, with the test detonation a month later. This timeline turned out to be a bit ambitious. Many experiments and technical issues had to be overcome, so after a while the team was authorized to delay the layer cake prototype explosion by a year. The detonation of the RDS-6S prototype was scheduled for August 1953. The year leading up to the test had been a tense one, with back and forth between the United States and the Soviet Union about which country had the upper hand in nuclear weaponry. In November 1952, the U.S. detonated Ivy Mike, considered the first test of a staged thermonuclear device. It used the famous Teller-Ulam design, a breakthrough design that successfully solved the problems associated with energy dissipation. Ivy Mike yielded a 10.4 megaton explosion, 700 times larger than a little boy atomic bomb. However, the device itself weighed over 70 tons, was the size of a two-story house, and cannot practically be used as a weapon. Nevertheless, Beria and the government put immense pressure on the scientists to come up with a response. The NKVD director sent 2 mathematicians to KB-11 as replacements if things did not work, and he reportedly said to the KGB general in charge of the program, "When we Bolsheviks want to get something done, we close our eyes to everything else. You've lost your Bolshevik edge. We won't punish you now, and I hope you'll correct the error. But don't forget, we have plenty of room in our prisons." Pleasant fellow. In August 8, 1953, a few days before the detonation, Georgy Malenkov told the Supreme Soviet that the United States shall not have a thermonuclear monopoly. Listening to his speech on the radio, the scientists realized that this bomb better work, or else. 4 days later, Kurchatov started the countdown at the Semipalatinsk test site. An observer recalls, "The intensity of the light was such that we had to put on dark glasses. The earth trembled beneath us, and our faces were struck like the lash of a whip by the dull, strong sound of the rolling explosion. From the jolt of the shock wave, it was difficult to stand on one's feet." Tanks had been tossed like toys. A 5-kilometer-wide lake was left behind. Birds fell out of the sky, their wings burned off, and their eyes blinded. RDS-6S, called Joe 4 in the United States, had been a successful detonation. Soviet scientists estimated the RDS-6S to have a yield of 400 kilotons. An American evaluation at the time judged it a boosted fission device, and thus incapable of scaling to arbitrarily high yields like quote-unquote true thermonuclear devices can. But unlike Ivy Mike, RDS-6S was small enough to be used as a real bomb. Soviet weapons designers at first believed that they could eventually scale up the layer cake design yield to 1 or 2 megatons, but they later did hit practical limits in how large the device can be while still being efficient with its uranium-235 and tritium. At this time, the team was chasing a far more compelling idea. While working on the tube, which had been inspired by Fuchs's 1948 material, scientists began talking about using compression to heat the thermonuclear fuel to millions of degrees and thus trigger a fusion reaction. This idea of compression came from a lab director, Viktor Davydenko, who repeatedly espoused it, but how to do this so-called atomic implosion. For several weeks, scientists played around with using the trigger atomic bomb's shockwave, or material explosion, to achieve this compression. Then, in spring of 1954, several scientists independently realized something. During an atomic explosion, the majority of the released energy comes in the form of X-rays. What if you can conduct this radiation energy to do the compression? This idea gained traction and was sent to the local computer center for simulation and verification. Known as Sakharov's third idea, though Sakharov was not the only one to come up with it, the idea is in line with the concepts behind the American Teller Ulam hydrogen bomb design. There is no indication that the Soviets used any intelligence from the United States. It came about organically. Fuchs's design had concepts of radiation implosion and was sitting there in the open, but neither the Soviets nor Americans used it, and its significance was not recognized until later. Work on the more efficient layer cake and tube bombs were abandoned. The Soviet team crafted a physical design to fully implement this concept of radiation implosion, leading to the device called RDS-37. The infrastructure and supply chain work done for layer cake contributed to the device's rapid development. RDS-37 was detonated in November 22, 1955 at the yield of 1.6 megatons. The two phases of the explosion can be seen in photographs. The Soviet Union had achieved the hydrogen bomb and parity with the United States far faster than anyone in the West anticipated. It is said that Ivy Mike's fallout helped point the Soviets towards how the bomb worked. Analyzing the fallout from the blast would have shown the presence of elements with nuclei exposed to high numbers of neutrons via compression, and that would have revealed the design secrets behind the Teller-Ulam design. This is a compelling theory. However, subsequent reviews of contemporary archives insist that the Soviets did not have sufficient skill nor technology to take these radiological measurements. What Ivy Mike and the subsequent 1954 Castle Bravo detonation did do was to tell the Soviets that such a massive weapon was indeed possible, and in order to achieve such yields, something else had to be going on. In many cases, an awareness that something else is going on is enough. Looking back, Soviet scientists feel immense pride in their achievement. In only a few short years, they had closed the hydrogen bomb gap with the United States, and in their minds, their work prevented a nuclear war. The rivalry between the two superpowers had now entered a new stage. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.